Hello folks, this is Tom from anti-proton.com. Today's topic, thermonuclear weapons. Well, not really thermonuclear weapons, that's only one type. Nuclear weapons in general. I'm going to give you a quick crash course, like really quick crash course of what they are. The reason is with North Korea being a really, really good super villain. If you notice, North Korea is like a super villain, like we'll get you next time. Because they keep doing that and threatening to like declare war with their crappy little nuke, I've gotten so many emails from people asking me like random questions about nukes, and there's a lot of myths out there, like piles of myths about nuclear weapons, like nobody knows. So I thought I would explain some of this stuff and clear up a few of these myths. So I'll explain these things quickly. The reason I'm in black and white is because color looks terrible with my black background, and these, by the way, just to let you know, are not degrees. I had somebody asking me like, oh my god, they said you have all these degrees. No, I don't. I have one degree, one college degree. That's all I have, and it's not even here. It's in the other wall over there. These are like from my United Nuclear Uranium samples. I just put them on the wall. So I just want to make sure nobody thinks that that's what they are, because I don't want to like falsely represent myself. Isn't it weird? I'm like one of the few people on YouTube that has a long, massive disclaimer at the beginning of my video, and yet I still get piles of emails of people that apparently still think that I'm representing myself as though I'm some kind of physicist. I'm not a physicist. I'm a computer scientist. I one day hope to be a physicist. I am not one yet. Got it? Oh my god, please. Anyway, so we're getting there. One day. But not right now. Right now, the only thing I can call myself an expert of is computers, and I am an expert at computers, and I totally say it too. But getting to the point. The point is computers. So let's get into. No, it's not. It's nuclear weapons. Nuclear weapons. Nuclear weapons. Big mushroom clouds. Okay. So let's get into it. Before I start, let me say one thing. One quick announcement. Just hold on. One quick announcement. This is a gamma spectroscopic dosimeter. You've all probably seen me show it before. My Polymaster 1703MO1B. My God, I'm speaking fast today. This little guy is a cesium iodide thallium dope detector, which makes it kind of like this device right here. It's another random gamma scintillator, because I just have them sitting all around apparently. Anyway, similar device, except this little guy has been on me for the last 2 days. It's not been outside of my body. It's been within 2 feet of my core for the last 2 days. And for 5 more days, it will be on me. I'm talking like when I'm in the shower, this thing's in a plastic bag sitting right by the shower, never more than 2 feet. I sleep with this thing. Why? Because I want to know what my actual dose rate is on my body throughout the day. And in 7 days, I'll have all that information. Now, I have a clean glove, but in just a second, it's not going to be clean because I'm going to handle radioactive materials. Anyway, let me show you this, and then we'll get into nuclear bombs. This is a piece of trinitite. What is trinitite, you might ask? There we go. Trinitite is sand, dirt, whatever, that was fused together and turned into glass. You ever heard the expression, we'll turn them into glass? Well, this is where it comes from. That's not a myth. That's actually real. And it came from Trinity, the first nuclear explosion. This is 1 gram or something. And I got this at a rock shop, and I found this, and the dude's like, oh, it's trinitite. And there's a lot of fake trinitite out there, just truckloads of fake trinitite. And I said, well, you know what, for $10, screw it. It'll be fun. I'll buy it and see. I put it up against a Geiger counter, and oops. Video pause there for a second. Sure enough, it was radioactive. Not much. But mildly radioactive. Just enough. Enough to be dangerous, right? Not really, though. And so basically, it's alpha, beta, and gamma, and X-ray. And I took this little guy, and I did gamma spectroscopy upon it, and lo and behold, it turns out to be real trinitite. Or at least, it is nuclear glass. It came from a blast, I guarantee that. I actually can't guarantee trinitite, but there it is. Let me get it up close. My computer's frozen up here. Well, not frozen up, but paused for just a few minutes a few times. I wonder if it's running something in the background. That's really annoying. Let's see how good my focus is. Oh, God, look at that. I've got good focus in this thing. Come on, you know you want to do it. Come on. Come on. There we go. I guess that's the best it's going to get. But it's, you see, it's shiny like glass, but it's nice and radioactive, so Anyway, basically put that should show you the heat of a nuclear blast. They're very powerful. It's ridiculous. Let's get into why and how and what they are and what they do. Take this off. Okay, we'll dispose of this. All right, so basically put cut the Geiger counter off. All right, getting into nuclear weapons. First, let me just give you the quick explanation of what they are and the two major types. Then I'll go into myths, and then after that, once that's done, I will then go into lengthy explanations of things, which will be fun. And you don't have to stick around for that part, because I know everybody always complains that my videos are too long. So fine, you don't want the lengthy part, cut it off. But not until you've seen the first two parts. They'll be quick. I even have them written up here on Notepad on my screen. I have a lot of monitors, and this allows me to try to stay on topic, because I'm terribly notorious about not being on topic. What is a nuclear weapon? A nuclear weapon is a weapon that is nuclear. It uses the nucleus of an atom. Remember in school you had electrons that spin? They don't really spin, not exactly, but close enough. You had neutrons that spin, and you had protons and neutrons in the middle, right? Like I said, they don't really spin, and it's not really like that exactly. But it's close enough, and that's basically what most people run around knowing. This is for the average person, so there you go. That's good enough. And these protons and neutrons have a lot of energy, and they're held tightly together by force, the strong nuclear force, and it's very strong. And then, in fact, specifically something called quantum chromodynamic binding energy. Apparently, I had some quantum chromodynamic binding energy in my chest there, burping energy. But anyhow, the force is very, very strong with this one. And if you present a neutron and you stick it inside of the nucleus of an already unstable atom, it will become very unstable. It becomes metastable is what it's called. It really starts blobbing all over the place. It can't stay together. It's like a waiter holding like trays of dishes, and you put a dish on top, and the waiter's like out of control, and they overcompensate, and they fall. And that's basically what happens, and the atom breaks apart. They say split. Remember, you split an atom? Well, they don't really split. They actually kind of become unstable and fall apart, but it happens so fast, nanoseconds, that it's like a split. That's why it's called splitting. Splitting the atom. It's not really splitting, but whatever. Close enough. It splits. So anyway, there are many types of nuclei that exist. There's all the elements that exist, and then every single element has dozens of isotopes that are like it. Like you can have normal, stable carbon, and then you can have an unstable and another unstable that have more or less neutrons in them. And so there's bazillions of atoms that are out there, different types. And only a certain number of them that go right down the middle, or actually kind of up at an angle, only certain numbers of them are actually good for fission, for splitting apart. Fission. That's when you split apart. Fission. So things that can go through fission are said to be fissile. That's close. Actually, there's fissile and fissionable. There's actually a difference between fissionable things, or things that you can make them go through fission. If you pound on them, you can make them, like uranium-238, natural uranium is fissionable. You can force it to fission against its will, but it ain't going to just do it by itself. And then there's fissile. That's stuff that likes to do it by itself. But let me tell you, if you leave it alone, it'll go do it in a heartbeat. That'd be like uranium-235. And of all the things that can go through fission, uranium-235, which is a naturally occurring isotope, by the way, and plutonium-239, which is not very naturally occurring isotope. Those are the two that are used in nuclear weapons primarily. Nuclear fission in a nuclear weapon usually occurs with plutonium-239 nowadays, which is made, by the way, from uranium-238. 235 is not used as much anymore. I mean, they still use it, but not like, they don't make like a uranium-235 bomb anymore. I mean, it'd be kind of stupid. You can use other things. The americium in a smoke alarm, polonium-210, for example, can be used, but these are not really viable. And the reason is, if you had a core of polonium-210, for example, the damn thing would, like this big, a big old core of it, would catch on fire. It'd be horrifying. You wouldn't be able to use it. So they only use those two. All right. Now, getting past that, those are fission weapons. Fission weapons go boom, boom. They're very powerful, ridiculously powerful, but they're dirty as hell, because only about 20 to 30% of that material is actually going to split, releasing energy. The rest of it's just going to get blown all over the freaking place. covered everywhere with nasty fallout. Terrible, terrible, terrible. I said I'd make this quick, so let me move to the next one quickly. Fusion weapons, the other type. In a fusion weapon, you have an initial blast, which ironically is fission. A small fission weapon goes off, and that small fission weapon has enough heat and energy to cause a second reaction to go off, and the second reaction is fusion. Remember I said atoms get pushed together? Fusion weapons are very, very, very powerful, and they can be made more clean than a fission weapon, but they're not actually always more clean. Trust me, ask people that were around with the first ones. They weren't terribly clean to start with. And what happens in a fusion weapon is you have a fission stage, which activates a bigger fusion stage, which can even activate, technically speaking, a third fission stage. You can, it's like fission, fusion, fission. You can have like stages of these things that activate one another. But any weapon that's a fusion weapon is a weapon that has fusion in it. So even if it's fission started, if it contains fusion, it's a fusion weapon. That's just the way they name it, okay? It's just how they do it. Don't ask me. I didn't name these things. If I had, I would have given them better names. But anyway, so Hiroshima and Nagasaki, fission weapons. The crappy thing that North Korea has, fission weapons. The Tsar bomb that went off in Russia, the big test one they set off, oh my God, fusion weapons. Whew, huge things. The stuff that America and Russia are always pointing at one another, fusion weapons, for the most part. Okay, I'll go into extreme detail of all that stuff in a little bit. But now for myths. But wait, disclaimer time. Everything I'm saying is available on the internet. None of this is secret type information. It's all available on the internet. You could just go look it up. So please, I don't want any of these people being like, how do you know this? Because I am literate and can read. So go read and you can know it too. Or you just watch my video if you're like, lazy like I am, you just want to hear. Okay, myths. Hollywood. This is your doing. Hollywood has made us think the stupidest things about nukes. Okay. Myth number 1. The core is cracked. We're all dying. Okay. Remember that movie Broken Arrow, whatever the hell it was, where the nuke falls on the ground and then the guy is trying to steal the nuke and he calls up the mission command place and he's like, the core is broken and we're all dying. Remember that scene? Okay. If the nuclear, you will never bump into a nuclear weapon, most likely. And if you do, even more likely you won't know you did because but if for some reason you ever bumped into a nuclear weapon and the core was exposed, you aren't going to drop dead. It doesn't put off that much radiation by itself. I mean, there's radiation coming off of it, but the thing is not putting off like tremendous doses of radiation. If it were, how could people wheel the things around in little carts? There's lead blocking it? Oh, really? It takes a lot of lead to block gamma radiation. Trust me on this fact. I have to block it all the time with my gamma spectrometer. That's just a weird thing that they talk about. And you remember James Bond in the James Bond movie? He holds the uranium pit in his hand. Well, actually, I think it was a plutonium pit. That's a little bit more realistic. Now, holding it in your bare hands, not a good idea. It's a nasty heavy metal, so it's chemically toxic, and it is radioactive. It is producing alpha radiation and gamma radiation and beta radiation as it produces daughters and stuff. It's terrible. But you could hold it. I would not consider doing it, but you could. Probably burn your skin a little bit. So basically, and the things aren't just natural like that anyway. They're usually like plated with gold and whatnot. So it's not something you would just find that way. So that's totally not likely to ever happen. I'm looking at my list. Number 2, guns and nukes. How many times have you seen it on the TV? There's a nuclear weapon in the room that they've like gotten away from the terrorist, right? And now the cops are all standing around shaking each other's hands. We saved the world. And one of them's like messing around with the gun, and somebody's like, "No, you better put that gun away. We're around nuclear weapons." You ever seen stuff like that in the movies? Okay, guns do not hurt nuclear weapons too much. I mean, if you sit there and shoot the damn thing, you're going to probably break it, but it's not going to go off. I mean, I guess it's possible. A really weakly constructed nuke, you could hit one of the lenses, one of the explosive lenses, and the thing, all the explosive parts would go off, and you would die, and everybody around you would. And the nuke still wouldn't explode, of course. It would like conventionally explode, but like the nuke part wouldn't happen. So in that way, I guess they're dangerous to shoot guns at. But the point is, you still most likely couldn't do it. Most warheads are contained inside a protective material to prevent stuff like this from happening. You really don't want the damn thing to go off. It's not like paper mache, okay? They put actual material around these things to protect them. Nukes are well guarded. Okay. I still wouldn't. I know I just said that was a myth, but I still sure as hell would shoot a gun at a nuke either. It makes me a hypocrite, but whatever. Okay, easy to detect. You know, if a person drives that nuke in here, we'll detect it. No, you won't. They produce a lot of radiation, but if you've ever run around playing with things like gamma spectrometers, for example, or my other ones, any of my other units, you know, even with huge, gigantic Bicron plastic, do I have one sitting around here somewhere? I usually have some Bicron scintillation plastic someplace. Well, whatever. Bicron scintillation plastic, those big sensors, and they put them all over the place. You know, like the guy in the subway recently that got caught for having technetium-99 in him. Yeah, those are sensitive. They are very sensitive. And if you wheel a nuke right beside one, yeah, it's going to detect it. But if you have it not too far away, it ain't going to detect it. Why? Because they're shielded. Okay, they produce radiation, but they're shielded. If you in a really sensitive detector, if like you know the doorway to get to some place with the nuke has you know like a high purity germanium detector built into it or something, or freaking like 50 cubic feet of Bicron plastic around it or something, yes, fine, it'll detect it. But this whole idea that you can walk around with a Geiger counter and walk near one and just pick it up, not so much. Because they do that in shows all the time. Oh, it's tremendous radiation, I can't believe it. Not really. If you got right up on it, I'm sure it would. This thing would probably go off if I got close to one, but I'd have to get pretty darn close to one for it to be detected. They just don't produce huge amounts. Going on to the next thing. Air detonations versus surface. I was talking about surface detonations of nukes. You know, it hits the ground and going off and everything. And somebody told me, they're like, oh, it doesn't do that. They're always airburst. So I looked around. Sure enough, everybody else thinks that too. Not true. Airbursts are useful, very useful. But ground bursts are also useful, and so are high atmospheric in space. A nuke is a type of weapon called a thermobaric weapon. Thermo, heat, baro, I can't remember the root exactly, but pressure, like barometric pressure meter. Yeah. So basically put thermobaric weapons like what's a good one? What's that big one? The Moab. You know the Moab, mother of all bombs. Remember the one they drop out? It's chemical. It's a gasoline fuel air bomb. Those things, they are actually thermobaric weapons too, meaning they explode and they produce a humongous amount of heat, which forces the air down. The air has a tremendous amount of pressure to it, and it pushes down. You get all of a sudden like a 20 or 30 psi change. All right, not so good for humans. We can maybe sometimes survive it depending on how close we are. Buildings get blown up. So that's what airburst is for. It's for just flattening all of the area around you. And then, of course, there's tremendous heat, fire, x-rays, and all that stuff. But when you're taking out an enemy silo, because remember, a lot of people don't get this. Russia or U.S., I'll say Russia and the U.S. Remember, I'm in the U.S., so I always think that Russia will shoot on me. But if I were in Soviet Russia, I would think that the American people would fire on me. Yeah, so each person's got their own opinion. Okay, so we'll just say good guy and bad guy. How about that? That way we don't mention a specific country. So the bad guy country, we always think that they would fire and try to blow up our cities. And they could, it's possible, but more than likely the bad guy country would fire. I'm not talking like a North Korea, I'm talking like a big country that's got a lot of nukes. Would try to first strike and take out our missile silos. Because if they take out our missile silos, then us, the good guy country, can't shoot back at them and they win, right? Why hit the people? Hit the silos. That's where the returning nukes are going to come from. And for that, you don't want an airburst because that's not going to take a silo out. I mean, it could, but it may or may not. So what you want to do is you want to hit the ground right beside the silo, and you want to make such a concussive shaking force that you dislodge the nuke and make it fall over. And that's what a ground burst is for. The nuke flies down right as it's about to hit the ground and it goes off. It doesn't actually hit the ground. It goes off right before it hits the ground. So ground bursts do occur, and they don't produce anywhere near as wide of damage because they're on the ground. Same as ocean bursts. You can blow one up under the water. They've done that before. They've blown them up in space. So typically speaking, things like air bursts are used to take out large populated areas, whereas high altitude creates electromagnetic pulses. Space just looks cool. And ground is designed to take out targets in the ground. Okay, I hear a fire truck. Next one, only 3 more. Small nukes. What's the small nuke one? This is a small nuclear device made small enough that it can be fit in your pocket and no one will detect it. Actually, it's gamma spectrometer, but if you've ever heard that on TV shows, that's BS. You can't make them but so small. And it's not because like the technology hasn't been refined enough. No, 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 no. There are laws of physics. You need what's called a supercritical mass when it all squeezes together. But so that it doesn't go nuts, you have to have a subcritical mass before it squeezes together. You got to have at least a certain size container. You can't get smaller. I mean, you can get suitcase size. That means a thick suitcase, but you can get suitcase size. You're not getting smaller than that, though. You just can't. I can't remember what goofy movie they had. There was a movie somewhere where they had a little tiny itty bitty nuke. I can't remember where it was, but it was just stupid. You can't get it smaller than a certain size. It just isn't happening. It's not our technology. It's just that it's laws of physics. So you got to figure out how to defeat them first. Neutron bombs. Next one. 2 more. Neutron bombs are designed to kill the civilian population and leave all the buildings intact so they could be inhabited by the enemy. Wrong. If a neutron bomb goes off, it's going to blow up all of the city. It's going to blow up all of the buildings and everything. Neutron bombs are a tremendous explosion. They have a different name sometimes. They're called enhanced radiation weapon. It's a better name because that's what they are. They're a nuke that produces lots and lots and lots of neutrons. It's called neutron flux. The point of having neutron flux is that tanks, remember we in America thought that the Soviets were going to come and get us with tanks, lots and lots of tanks. Tanks are somewhat immune to, not immune, but they're more immune to radiation and blast and stuff than a lot of other things. The T-90 might have like lead foam armor on it, for God's sake. It can survive a hell of a lot of radiation. But neutrons go right through that armor, and they tear everything up. I mean, they're not so good for your health. And as a result of it, an enhanced radiation weapon, a neutron bomb, was designed to kill tanks and things like that, or heavy bunkers and so on, okay? So that's just a dumb, I don't even know where that ever came from, this idea that the buildings would be there. I mean, it doesn't even make sense if you really think about it. So, not true. If the radiation produced from the nuke is so terrible that if one goes off anywhere on the Earth, it will kill us all. There's been over 1,000 mushroom clouds floating up into the sky on Earth. Over 1,000 of them. 1,000 of them. 1,000 of them. So that should give you an idea of how much radiation is put off. It's a lot, don't get me wrong. Nukes that were set off in the Pacific Ocean had fallout that was powerful enough to kill if you were near it. I mean, thousands of square miles of area was covered by it. But a lot of it dissipates fast. Some of it doesn't. Like the cesium-137, that's going to be there for 210 years or whatever 7 times its half-life is, okay? And other parts are going to be there for longer. You know this. This is duh. Look at Fukushima. Does that look like it's going away? No. But there's a lot of short-term, really, really short-lived isotopes like radioiodine, for example, that are really terrible initially, but go away quickly. And so that's why if you can hide somewhere for a while, a month or two, then the radiation levels drop tremendously. So even if we had a full nuclear exchange, it's not like the world would end. It would suck. Don't even get me wrong. I'm not downplaying it. It would suck. Life would change as we know it. But we would not all die. Oh, yeah, we'd probably die. I mean, like 3 out of 10 of you might live. But I mean, so don't get me wrong, horrible, end of days, etc. But it wouldn't be like the movie On the Beach. Everybody's taking the cyanide pill, it wouldn't be like that. You would go and you'd hide for about 2 months, and the cloud would go away, and that would be that. I mean, people who were hit by Hiroshima, and it rained upon them, they're covered in it. They dusted it off, and then they lived 80 years old. I mean, and a lot of it comes down to things like cancer and the probability of cancer killing you. Cancer may kill you, may not kill you. So I am in no way, shape, or form downplaying radiation. I am in no way, shape, or form suggesting that it's safe. It is not safe. But it is not true on the other side that you would all just drop dead either. So just kind of like keep that in balance. Was that all I was going to talk about? Well, that's all I can think of. So concludes the introduction and the myths. Now, this is the boring part where I go into explaining some more details about stuff. I suggest you stick around because this is the fun part. But for everybody else, you can scoot. All right, just to give you a little bit more information about them. Most countries use fusion weapons nowadays. Now, the reason for a fusion weapon is you can use a lot less nuclear material potentially, and they can be cleaner. Let me start with how a fission weapon works. Maybe that'll explain better. The fission weapon has a subcritical mass of, let's say, plutonium-239, meaning a subcritical means that you can hit it with neutrons and it will go through fission, but it's not going to do self-sustaining fission. If you were to squeeze that subcritical mass tighter together, you hit a critical mass. Critical mass is the amount of material required for a self-sustaining reaction, basically put. But it's reasonably controllable at that point. Like, for example, nuclear reactors reach a criticality inside of them. But when you squeeze it tighter together, like really tight, you get something called a supercritical mass. And a supercritical mass can undergo fission by itself, based on something called spontaneous fusion. Spontaneous fission. See, I said fusion when I meant fission. Things like your smoke alarm in your house undergoes spontaneous fission all the time. Like your smoke alarm, well, not all the time, but per year, your smoke alarm will undergo several minor fissions. Like an atom will, catch a neutron and come apart. So, inside of a fission weapon, you have a subcritical mass, and you have explosives all the way around it, like conventional ones, like C4 sort of explosive, right? When they hit the button, those explode and they compress that core together. Now, you have you have the explosives, and in between the explosives, you have something called a pusher. And it's a thick material that's hard to break, to put it mildly. It's a material that can kind of, it serves like a intermediary between the two, like a wadding in a gun. If you ever loaded a gun, you get wadding inside of it, and it squeezes that together to make it tight. And then in between the explosive, the pusher, and the pit, which is the material in the middle, the subcritical mass, you have something called a tamper. And often the tamper is also a reflector. You could also have something called a reflector too, but usually they're the same thing. And you'll use something like uranium-238. And what happens is, as everything squeezes together, this tamper is very dense, and it gets a lot of momentum moving forward because the explosion's pushing it forward. It's got a lot of momentum squeezing it. And all of a sudden, that mass hits the center, and about the same time, neutrons are injected. Or in older designs, you had neutron source inside of it, like a beryllium and a polonium-210 or something, and it would get squished together, and neutrons come out. So either way, and when this happens, you get a reaction going, fission. Atoms are splitting and shooting other neutrons out, which are affecting other atoms, and so on. Now the problem is the heat this generates is tremendous, and it will blow apart the core. It has so much kinetic energy, it can stop the implosion and cause an explosion. But you don't want that, because the longer you hold that thing together, remember firecrackers? If you have it in your hand, it explodes and hurts, but if you squeeze it, it blows your hand off, firecracker. Same idea, you want to squeeze that sucker up. And so you use that tamper, and that tamper is really, really, really massive and heavy. And for that matter, the pusher is pretty heavy too. And they've got so much momentum, it takes a while for them to slow down their momentum and then to change and start going the other way. They slow down and come to a stop and then start going the other way. And at that amount of time it takes that to happen is increasing the amount of fission going on there and jacking it up from 5 or 10% to maybe 20 or even higher percentage. And that's going to cause a really, really powerful burst of energy that goes flying out every direction. The casing incinerates and the explosion moves out every way. That's how a fission weapon works. In a fusion weapon, you have the same thing, but what happens is as that explosion occurs, you can channel a lot of that energy into a second core. And that second core will have something like plutonium around the outside. And on the inside, you'll have something like deuterium, which is hydrogen-2, heavy water. And in between, you'll have something like lithium-6. And when that heat hits that lithium, it causes that lithium to turn into tritium. Well, some of it turns into tritium. And that gets blasted and injected into the core, and you have fusion that goes off, right? This time I said fusion right. Tritium and deuterium come together to produce helium-4, a neutron that has about 14.1 million electron volts of energy and 1 or 2 million electron volts of energy for the helium-4 atom. And then there's a total of 17 point something or other off the top of my head, additional million electron volts of surplus energy. So actually, no, that's the total sum of it all right there. It goes off every direction. And as that's going off, as that fusion's occurring and going off, it'll cause that plutonium around the outside to undergo fission as well. And so you end up with a fission device. That's actually one of the most common places. That's the common thing you deal with right now. Those can be clean or dirty. And clean or dirty has a lot to do with how much of material is left over afterwards. If that tamper, remember the device that slows the explosion down, if that tamper is made out of something that can also become fissionable, or if that the casing and the outside of the fission thing, if those are made fissionable, it increases the dirtiness of the nuke. Lots more material is left over. It also increases the yield tremendously. But if it's made of not so fissionable stuff, like tungsten carbide or whatever, it's going to reduce the amount of dirtiness. So it depends on what you want. You want to blow them up, or do you want to do it PC, politically correct? But dirty is not the way to go. Trust me on this. You want clean if you can. Now, getting into things like North Korea. I wonder about North Korea. They do have a crappy little nuke, right? 7 kiloton weapon. We're not talking like superpower, but it's still a nuke. I mean, it's like a person with a gun pointing a gun at you, but it's a 22 caliber. Oh, it's 22. It's a joke. Haha, but it's still a gun. Even a BB gun hurts, right? What I worry about with them is whether or not they will develop the technology to use that small nuke to initiate a bigger fusion weapon. Probably not anytime soon, but you don't know. We hope that they don't. We hope that they stay as ignorant as conceivably possible. Yeah. So basically put, this is a little bit of information to help you. And I'm putting this out here because people seem to be very misunderstanding of all of this, and I think it's very important for people to know how it all works. And last disclaimer for you. It doesn't matter, even though all this information is completely public. Go to Wikipedia and look it up. Keep in mind that even though it's public, it doesn't matter. Most physics students coming out of school would know all of this too. What prevents people from having these things and making them is the material. You can't get it. It doesn't matter. You can't get it. You can't collect parts and make it. Okay, that one guy made the little reactor. Remember the radioactive Boy Scout? He made a reactor, yes. But you can't make the boom boom. He can't do it because the amount of energy, the amount of time, the amount of buildings and people and everything required to enrich. It's tremendous. Look at North Korea. Look how much money they spend, and they only make a little tiny bit. Well, they make about that much every year. Okay, so that's why it's not too much to worry about. And there's not that many countries that have it. Oh, and kudos goes out to South Africa, the only country that I know of to create a nuclear weapons program, make successful working nukes, and then have the decency to give them up. Rather, the luxury to give them up. I should say the luxury, not the decency. The United States would probably like to give them up, but I bet you it can't. Same with Russia. Honestly put, if South Africa gives up theirs, they don't need to worry about anybody attacking them pretty much. So anyhow, this has been Tom from anti-proton.com, and I will come back to you in 5 more days, plus or minus, and give you the answer to my dose rate. Oh yeah, and in case you're curious, when I hold stuff like the sample over here, I'm going to separately calculate how much time I spend holding that. And after I'm done with this and I've recorded it and documented it, I'm going to then take this, reset it, put these samples near it for the exact same time I was holding them, so you can figure out what my hand dose was, which would be tremendously less. So, yes, it's 33 minutes, so not really that short. This is Tom from anti-proton.com, and bye-bye.